Good morning. So in this video, I am going to explain different compression techniques, right? The first one is run length coding. So this one also lossless coding, lossless compression technique. So here interpixel redundancy has been addressed here, right? So that means this one is reducing the interpixel redundant data. Okay. Now here that can be reduced by the what is that? Size of a repeating string of symbols, right? So here if you see the example, so here there is the code here. So here 1111100000001, this is the message. So take the example here, just count here, repeated data is there, right? So this one is repeated, so that means how many ones are there here? 5. What is the value? 1. 1 is repeated. So here 5 times. Now 0. 0 is repeated in 6 times. And 1. That is here 1 time. So that's why here we should count the particular symbol and then you should place that symbol here. That means here instead of transmitting 5 symbols, I just transmit 2 symbols only here. So that means if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, approximately 12 symbols to transmit this one. So I just use 1, 2, 3, 4, 5, 6 only. 6 symbols I may use that one. Okay, right? So here in for next example, A comma 3, B comma 6, C comma 2. So in this way, instead of transmitting this one, I just transmit this one. Okay, so this is the one here. I may use here again Huffman coding also, right? So after what is that? Getting this one, what is that? I can, after reducing the redundant data, interpixel redundancy here by using this technique, I may use the Huffman coding for transmitting B comma 6, right? A comma 3, like that. I may use the what is that? Huffman coding for variable length coding, okay, for providing variable length for each symbol. Okay, now here that encodes a runs of symbols into 2 bytes, right? Symbol comma count. So it can compress any type of data but cannot achieve high compression ratios compared to other compression methods, right? So why here? That means suppose if continuous runs are there, it is okay. But if here is a 1 and again 0 and 1 again 0, now what we can do in that? A, B is there, then C, 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 then A is there, then again A, B, B, A, like that. Then that means if you, in such a case, this one takes the more, what is that, bits, right? So that's why in such a case it may fail. But other than that, continuous runs are there, continuous or the continuous symbols are there. So it is the good one, right? So now, run length encoding is a technique used to reduce the size of a repeating string of characters. Okay, this repeating string is called a run. Typically, RLE encodes a runs of symbols into 2 bytes, count and symbol. Okay, RLE can compress any type of data. It cannot achieve high compression ratio compared to other compression standards. Repeated. So it is easy to implement and easy and quick to execute. Run length encoding is supported by most bitmap file formats such as TIFF, BMP, and PCX. These are the file formats actually. So these are supporting the are using the run length encoding. Okay, right? So now just another example. So if the data is like this, you just encode like this. Okay, right? Just use the count and then take the symbol. So by combining the Huffman coding, we can use this one, right? Now the next coding technique is bitplane coding. This one addresses the interpixel redundancy. What is that? Interpixel redundancy. So here that process each bitplane individually. Okay, of course this bitplane coding is similar to bitplane slicing, which is discussed in what is that, enhancement unit, right? It's okay. Here the bitplane coding means here we just decompose the particular pixel, what is that, bits into what is that, how many bits are there here. If suppose 8 bits are there, 8 planes are 8 planes are decomposed here. right? It's okay. That means here decompose an image into a series of binary images, compress each binary image, so by using run length coding. So here one gray image is there. Image has so many pixels. Each pixel is represented in n-bit data. Each n-bit data. Now bitplane coding means that n-bit data is decomposed into n bit planes, n planes, right? So that means that a gray image is decomposed into n binary images, right? So based on that, each binary image is observed again. In that continuous string of symbols are there. By using run length coding, I can reduce the, what is that, number of bits. That means we can compress the binary image, right? So now here, what is that? An m-bit grayscale image can be converted into m binary images by bitplane slicing. The intensity of an m-bit monochrome image can be represented in the form of the base 2 polynomial. Of course, we know this one. What is that? So this is LSB and this is the MSB. am minus 1 2 power m minus 1 plus am minus 2 power m minus 2 and so on. a1 2 power n plus a0 2 power 0. In this way, we can represent the particular gray level intensity in the form of, what is that, binary form into the, what is that, decimal form. Okay, now here, so see the example here, 2 by 2 image is there, right? So here only 4 pixels are there, 4 pixels. So here each pixel is represented in 3 bits. So now 101, 110, 111, 011, just an example. Now here this image is decomposed into 3 images, 3 binary images by considering only here individual bits. So if I take the first MSB bit here, 1, here also take 1, here take 1, 0. That means 1110 is the, what is that? Is the, here if I take representation like A2, A1, A0. This is the A2 image. What is the A1 image? 0, 1, 1, 1. What is the A0 image? 1, 0, 1, 1. Like this, right? Then an m-bit grayscale image can be converted into m binary images by bitplane slicing. These individual images are then encoded using run length encoding. Okay, right? So that is nothing but bitplane coding. Okay. So okay, here the next one is lossy methods. Lossy methods means we have so many techniques. So block truncation, lossy predictive transform, subband, fractal, vector quantization. In our syllabus we have the, what is that, transform coding and predictive coding also, right? Transform coding. So now focus on transform coding. So here the lossy compression. So that means quantizer is involved here, right? So mapper is there, quantizer is there, then symbol encoder is there, right? So okay, here what is the encoder block and what is the decoder block for the lossy compression? What is that? In the transform coding. Transform coding. So here to transform the image into some other domain today, and also to reduce the interpixel redundancy. This one is for reducing the interpixel redundancy. So of course majorly, and then here the image is transformed into the another domain. That means spatial domain is transformed into the frequency domain. So see the encoder block here, input image of size n by n. Just construct n by n sub images, small n by n. That means if I take 100 by 100. So if I take 100 by 100 size of an image, you just decompose that image into 10 by 10 size of images. Am I correct? So that means if I take 10 by 10 size of an images, so 100 by 100 size image is divided into 10, 10 by 10. Okay, like that. So just construct n by n sub images, then apply the forward transform on this. That means what is that? Frequency domain representation. So now based on this transform coding, what is that? We can reduce the interpixel redundancy. Then use the quantizer. So quantizer reduces the relevant information or psychovisual redundancy. Then use a symbol encoder. You may use any symbol encoder encoding technique like Huffman coding, arithmetic coding, anyone. So use that one. Then you can get the compressed image, right? So after getting compressed image, should to decode the particular what is that image from the compressed image. So here we have to perform the reverse operation. So here symbol decoded. So use the decoding techniques here. Now inverse transform. That means here convert the particular frequency domain representation into the again spatial domain. So use the inverse transform. If I use DCT here, if I use the IDCT, if I use here anything Walsh here, inverse Walsh like that. So here again merge the n by n subimages. Merge the n by n subimages. That means this is the symbol decoder. This is the inverse mapper, right? Inverse mapper. This is the mapper. So in reverse operation, that means the forward means here inverse. Here construct, that means decomposition means here merging. So merge the n by n subimages, then you can get the original image, right? Okay, but here is the output is the lossy. Output image is not equal to the exact original image due to the loss of certain information. So since here quantizer is used, right? This is nothing but transform coding in lossy compression. Thank you.